Okay, students, so just to carry on here with some of these basic commands. Um, these are, again, commands that I think are very useful just for handling really large files, because frequently you need to kind of take a look in a file to orient yourself to check the format of the file. It's kind of a sanity checking thing to do. Let's go into the FASTAs directory here, and you know take a look at, say, this first 25 lines of this file here. There they are. We can do that with the head command. We can do the same with the tail. The less command here, we've been using that. That just steps through line by line. The more command, that steps through a text file page by page. Let's do a grep command to have a look at what the identifiers are in this FASTA formatted file. And here, so this matched every line that had and dumped to your terminal, all of the lines that matched the sideways character. I'll leave some of these other grep options for you to pursue in your homework, but grep is one of the most powerful Unix tools you'll learn how to develop, and I think it's one of the most important ones from the perspective of command line skill. Let's go over here to tables, clean up a little bit. But one of the commands here that we'll use is cut. This is a way you can easily slice and dice a table. Here I'm just showing you a 3-column file here that has the common name of the great apes, the species scientific name of the great apes, and their brain volume here. It's just a small table. And one of the useful things to know about a table when you first begin to work with it as a bioinformatician is to know what the delimiters are between the fields or the columns. Okay, and one simple technique you can use on a Ubuntu system is to use cat-a. I believe on a Mac it's cat-et will effectively do the same thing. But here, notice now the hat and the I between the columns. That means that there's a tab there. So this is a tab-delimited table. And the end of line character here is a line feed or a \n, although that's hidden from view. You don't ever see the line feed or any end of line characters in a typical terminal anyway. And so just to alert you that different systems use different line feeds, and that this is something, if you're sharing files with a PC user, or if you're a PC user yourself and you find yourself working in a both Windows and Unix-like environment, you'll run into issues with parsing text files. Okay, and this is one reason I personally like to work only in one environment, because of issues that you run into like this. So this is a line feed in Mac and Unix. The old Mac used what's called a carriage return, but in the newer OSs have adopted the Unix-like line feed. PCs use a combined carriage return and line feed command for their end-of-line characters. Just a heads up there, because that's a common gotcha particularly when you're working in different environments. So let's say we wanted to extract the second column of this file. There you have the species names in scientific format from column 2, using the field option, which extracts the second field in this case. Okay, so this is, I'll leave that for you to do a little bit and explore a little bit more with in your homework assignment. Meanwhile, let's carry on here. So one of the concepts here that we've already kind of started to use, although I hadn't given a formal definition, is the idea of these I/O streams, piping, and redirection. So any Unix program has 3 streams: the input stream, called standard in, and then it has a standard output stream and a standard error stream. So by default, when we just do cat and the name of the table, the program is taking from the standard in is coming from our command line terminal. So these text here that we're typing in is coming in in standard in, and when we execute the program, standard out by default here is being written to the terminal. Okay. So what about standard error? Well, standard error, there are no errors when we in this simple command, and so nothing got written to the standard error stream. But what if we just type bad command? Okay, there is no command called bad command. There is no binary called bad command. And so what we get is, again, written to your terminal is bad command, command not found. This is the output of the standard error. Okay, but notice by default it also is being written to your terminal. Okay, that is the default place where standard error gets written to. So we can redirect these error streams and standard output streams into files if we'd like. So let's do echo hello world and redirect using the sideways character here the output of standard out to a file. Let's just call it standardout.txt. So what's in standardout.txt is hello world. So what we did is we redirected the standard out from its default location, which is to get dumped to your terminal, into instead we captured it or redirected it to a file called standardout.txt. We can do the same thing with bad command here and redirect the standard error using this convention of putting a 2 before the sideways caret, and we can write that to say a file called standarderror.txt. Again, notice that bad command did not get written to the terminal. Instead, it went to a file called standarderror.txt. So that is now here. So we can combine these then into a single command where we can do echo foo bar. We can write it to the standard output to standardout.txt and the standard error to standarderror.txt. We execute that command, and this also illustrates a second point, but the contents of standardout.txt is foo bar. But that's important to notice that a minute ago we dumped to that same file hello world. We rerouted it to standardout.txt, but now it's gone, right? Because the contents of that file is foo bar only. So this just illustrates the point that when you use these operators, that they overwrite the file. Okay, we are not appending to the files, we are overwriting them. So what happened, so when we did this command here, we had echo foo bar, redirected the standard output to standardout.txt, the standard error to standarderror.txt. Well, there were no errors in that file, so if we look in standarderror.txt, that's a new file that got generated by that command, and there's nothing in there because there was no errors. Okay, so this is a common way to use when you're generating log information and when you're running programs, is to capture the standard error and the standard out in different files. So the standard out, it's common to dump the output of a program to standard out. You can capture it here, okay, but you can also capture it separately from the errors that are being generated due to, say, bad commands. Okay, so one other thing, I showed you how these operators overwrite the files. Okay, so they lead to creating a new file called standardout.txt that will overwrite if that same file is already there. And that's standard behavior, it's expected behavior, you need to understand it. And I wouldn't recommend modifying or configuring your machine to do anything different, because this is kind of default in the Unix world. is to have this behavior and it be the expected behavior. There are ways to get around it if you want to protect a particular file from being overwritten, but I wouldn't recommend it. Except in exceptional circumstances. So one other thing I wanted to point out here is this, how do you append to a file? So let's look what's in standard out right now is foo_bar. So what if we don't want to overwrite the file, but we just want to kind of append, new information to that file without overwriting it? We can do that by echoing and using the double sideways caret, and we can write then to standardout.txt. And now what do you think will happen? Well, now we have both foo_bar. Here we just had foo_bar. Now we have foo_bar and hello world. So we appended hello world in this command here to that file using the double sideways caret. Okay, so those are pretty trivial examples for redirection. So how does piping really work? So let's go back over to our FASTAs here, and let's just let me just give you an example. We can use the zcat command here to take a peek at that Volvox. This is a genome of group of algae, sorry, called Volvox. This is the FASTA file for the genome. We can pipe the output of zcat, which is to, by default, write the standard output to the terminal, just like cat. But what we can do is now pipe that standard output rather than to the terminal, we can pipe it to another program. So let's do the simplest thing, which is to just pipe it to less. So less is then reading from standard in now. Okay, so less is reading standard in, which was the standard out of zcat. And there you see for the beginning or the top of the file. We can do something a little more interesting. We can say look at the identifiers from that file. Here what I'm doing is we are using zcat to dump to standard out. The standard in of grep, okay, is specified here either by default without specifying an argument at all. So the standard behavior of grep is to say grep, the pattern that you're trying to match, and a file name. But here we don't have a file because we're going to use zcat to pipe its output to the standard in of grep. We can specify that explicitly with a dash or a minus, or we can just leave it out, because if grep doesn't find the argument for a file here, it knows to look in standard in. But let's be explicit here for now. And now let's pipe to less. And now what we're doing is grepping out, any basically line that contains this sideways character, okay, and matched our grep pattern match here. We can also, rather than doing this, we can say count up the number of different identifiers in this particular genome, and there's 434. So this is a fairly broken up genome compared to, say, a human genome that has 23 nice chromosome sequences in its FASTA file. This genome has 434. They're not 434 chromosomes, it's just that they haven't been assembled. Okay, they're all part of these scaffolds. Okay, so we don't actually know how they orient or how they line up along a chromosome. Okay, so hopefully that you'll get to explore this quite a lot more in your homework, so I won't do anything more with it now, but just the concept of standard out going to the standard in of the next program, which generates its own standard out, which goes to the standard in of the next program. This is the basis for Unix piping. And it allows you really to customize your analysis from the command line very easily. Okay, we're not just capitalizing on the function of one program, but we're stringing together the functions of many programs, and in this way customizing our analysis. So I think I've covered all of the important subjects I wanted to cover there. So let's switch topics to working in a Unix-like environment with variables. Okay, so this is another important topic. So what is a shell variable? Well, shell variables are variables that contain information that either you've defined or become predefined by various configuration files that get executed when you start your computer or when you open a terminal. So what variables are sort of defined on my system at the moment, here they are. By convention, these variables are given all capital letters. So we've seen home already. And you should do the same on your system to get a sense of what variables are there. How are the variables assigned? Okay, so how did those variables get to be assigned? Well, the answer is that there's these configuration files called profile, bash profile, and bash rc. Notice that they're prefaced with a dot, so they're hidden files on your system. But what happens is that when you start a computer, that opens what's called a login shell, and it executes that file, which inside of that file has variable definitions that configure your system. And in the case of Ubuntu anyways, that file also executes this bash rc file. That's what sourcing is. We can talk about that in a second. And this is how all of your variables get defined. Okay, it's also true that bash rc, every time you open a new terminal, when you open a new terminal, I can just open one here, using a shortcut. When I just did that, the bash rc file got executed, which then defined a new set of variables, okay, here in this particular terminal. So on a Mac, it's slightly different, but the concept is the same. It just has a different order of events. These files exist on may or may not exist. Actually, I think Ubuntu doesn't have a bash profile, but Unix generally knows to look for bash profile and profile on the startup of the computer, okay, and bash rc on the startup of a terminal. Okay, this is for the Mac. So the essential concepts here are essentially that there's these hidden files that have variables that when those files get executed, your environment gets configured. Those are these ones here are what are called user-specific configuration files. Then you also have system-wide. So each user on a shared cluster, for example, will have these files executed when they open terminals or when they log into the computer cluster, whereas system-wide files are files that get executed. They're the same for everybody, all the users working on the system, and those files are typically found in root etc directory. Okay. Again, these also just work to perform the function of configuring your system. So how do we assign variables ourselves? Okay, so this becomes important when we're working in a Unix-like environment. Sorry, just having a issue here. I lost my terminal. So in this system here, in a Unix-like environment, okay, again, we want to define our own variables frequently, particularly when we begin writing shell scripts. Okay, so how do we define variables? Remember, I told you that by convention, we give variables the all capital letters. So what I'm doing here is on the left is the variable, on the right is the value we're assigning to that variable, and notice that we're separating it with an equal sign with no white space. Okay, white space will cause a problem if we try to define it here. Your system is looking for a command in its search path called first, which of course doesn't exist. Okay, so we can then query the contents of those variables by using the $sign, prepending the variable name with the $sign, and in this case we're just echoing first and last, and of course we can combine these, put a white space in between. Okay, so this is how we define variables in a Unix environment. I won't go into more detail here. I'll just, we can just point out that when you open another terminal here, and the question is are these variables that we defined over here in this process, are they defined over here in this alternate process? What do you think? Well, the answer is no. Okay, these variables are limited to this process, and this is a separate process where, again, like bashrc got executed when we opened this terminal, and a different set of variables got defined than are defined now in this process here. So some of this gets more complicated. That's just to point out that things might be a little bit more involved than you might imagine. You might want to, as you go along here, we'll, learn about the export function, which is a way of, passing essentially the variables from one process into child processes. But for today's lecture, we won't go deeper. Okay, so let's quickly switch here now to writing our first shell script. What is a shell script? Well, a shell script is really a script that contains a series of commands that all get executed in succession. One command, so we in a shell script, will not get executed until the previous command has been completed and issues an exit status to the computer, which tells it that it can now proceed with the next command. So let's open a simple text editor here called Nano, and let's specify that the shebang line here at the top of the file. Let's write a small program here. And save the file. We'll call it temp.sh. I already had one there because I was trying this earlier. And yes, we've written our first shell script. We can, view it. There it is. So what is this shebang line here at the top? Well, the shebang line tells the interpreter, or tells the kernel rather, what interpreter to use to execute the program. And so the pound exclamation point here at the beginning, the kernel uses this to recognize that this is a statement that will define what interpreter it should use to execute this particular script. So other scripts, when you're writing a Perl script, will have, say, user bin Perl here, or say user bin Python, or other interpreters that can be used to execute programs. Okay, but here we're specifying explicitly that we want to use root bin bash. So we have to change or give this script executable status in order to execute it. Technically that's not true because there's other ways to execute that I'll show you, but we can assign that script executable status like so. We can then just simply type the name of the script and it executes. Okay. Another way to do this is to simply not change the exit status, okay, or excuse me, not the executable status of the script. Let's make a second script that we call let's call this temp2.sh, and if we just type, we can explicitly say what interpreter we want here, and in this way we don't have to actually change the executable status of the program. Okay, so that can be useful. And in this case, because we're explicitly stating the interpreter, what happens is that excuse me, I actually executed the wrong file, which worked fine, but in this case, if we just do temp2.sh over here, it wouldn't work, right? Because we didn't make it executable. but we could execute temp2.sh by specifying bash, because we're telling the kernel explicitly that this is the interpreter that we want to use. Okay. Okay, so this is kind of how to write a shell script and how to execute it. I would recommend probably just sticking with the convention for now of doing the chmod plus x on your shell scripts and then executing with this syntax here. Again, with this you should include the shebang line at the top of your shell scripts. Okay, so once again, this is a typical shebang line here that it tells the kernel, which interpreter to use. So one other thing that's important here is when you're executing, you can also source, a script, and that again has to do with the scoping of variables. So if you define a variable in a script by default, let's just do this really quick because I think maybe this will head off some questions you might have. Let's define my city equals NYC. Okay, so let's define that variable in this temp.sh script, execute it. Okay, and now what do you think? Will my city be defined? The answer is no, because this opened a second process, a child process, that does not pass to its parent process, any variables that got defined inside of the shell script. Okay, so instead, let's do something different. Let's source this shell script temp.sh. Okay, and then when we do that, if we echo my city, there it is. So this is important because the third method here, okay, you can go back and rewatch this video a couple of times or this section if you want to see what just happened there. I would recommend that because there's a third way to execute a shell script. I've shown you the way that you can make a script executable. You can execute it using bash, or that explicitly says what interpreter you want to use, but you can also source a script. Okay, which does require the shebang line at the top of the file, but what it does is it executes it in the current process's environment. Okay, it does not spawn a child process which has its own unique set of variables that don't get passed back to the parent process. So another way to say this is that sourcing a script, okay, it's essentially like copying the text from inside the shell script file, okay, and actually typing it directly here in this process. It is not that is not the same as executing this file in which a new process gets started and new variables are getting defined, and they're not passed in that. If you just execute the script, they're not passed back to the terminal or the parent process. You have to source the script in order for the variables that you define inside the script to be defined back in your terminal. Okay. Okay, so these are some basics, but hopefully that's fairly detailed. But hopefully you will take away something from that and have learned a little bit about how your Unix environment works. So finally, I just want to walk you through some basics of working remotely and how to transfer data. We've started already with the SCP, but one thing we can do here is let's open a new terminal and let's go to the course. Let's go to another machine here. Let's go to a machine I have elsewhere. And here we're simply SSHing, right? So using SSH, this is the secure shell. I am now logged into my computer at a different location, and my directory structure here is different. I can take you into a directory here. I am essentially working on a different computer than on the one that I'm giving this lecture on, and you can't even tell that I'm working on a different computer, okay, because by using the secure shell, we're logging into a different system, and we're manipulating it as if I was actually sitting there physically typing on that system. So secure copy, you've already had some exposure to this. By the way, the secure allows people to not peep in either on your shell commands or on your files that you're copying. A secure FTP, this is a little bit like secure copy, it's just a little bit more sophisticated and allows you to issue other commands than just copying. Okay, you can do other things with SFTP. Finally, wget, this is a command, at least on Ubuntu, that allows you to download files from FTP sites or hosts directly from the command line. That's very useful. So, for example, I write shell scripts that do all my downloading for me, so I string together a series of wget commands that will define, say, extract an entire set of flat files from a database, for example, and I can do that all in a shell script. I then have a history, in the shell script of exactly what commands were issued and where all of the files that I downloaded, were from. Okay, so wget. I'm not sure. I don't think a Mac has that, so you'll have to look that up if you're working on a Mac. Finally, when we transfer files, okay, in NGS analysis, we're working with very large files. Okay, so let's go to, I think here I have in a directory here some pretty large files here. I have 24 gigs just caught up in these few files here. When you're moving these really big files, like FASTQ files, especially when you're moving them, say, from one cluster to another, say via some connection, it's important to validate the integrity of the files. Okay, so the way you can do that is, on my system, it's MD5sum. Let's just take one of these smaller files here, and I'll show you how this basically works. This takes a second. But what the MD5sum is it issues a unique barcode, okay, for each file. Okay, well, this could take some time. But this barcode can be used, say, to query get a barcode for that file. Say before you copy it from one location to another, and then after, and you can compare the results. Okay, so let's now copy that file. Say, one directory up. Okay, and then let's do an MD5sum on that file, one directory up. Sorry, my connection here is crapping out. So yeah, I think oh, here we go. So if we do the MD5sum on that file that we just copied, we can compare the barcodes. This is a unique, what's called a checksum or a barcode, and here you can compare this one to this one, and they're in fact identical, right? So this barcode, so nothing happened, right? We just confirmed that in that copying of that file, that the file was not corrupted, it did not change. So whenever you're moving files around, okay, and this is MD5 checksums become very important as a way of validating the data integrity. Okay, so that's it for this second lecture in week 2. I'm going to encourage you to go over and have a look at the homework. I think you'll find it to be fairly simple, but it could take you some time to work through the tutorials, because the best way to learn the Unix command line is to really just sit down and just start working the command line yourself and playing around with some of these features. The tutorial I've given you from the Corf Lab at UC Davis is geared specifically for bioinformaticians at the entry level, and I'd like you to spend a considerable amount of time working through that tutorial, executing the commands on your own system. Okay, so in the meantime, thanks a lot, and we'll see you later.